Hi, we're going to start chapter 16 in your text, which will be a huge shift from what we've been doing. So we've been looking at equilibrium and applications of equilibrium, and now we're going to look at the physics behind equilibrium. So let me share my screen. So this is chapter 17 in the new textbook, chapter 16 in yours. So we're going to talk about why systems change in the direction that they do and why equilibrium exists where it is. So why does change stop happening at equilibrium? So it has to do with the laws of thermodynamics from physics. So this is an area of physical chemistry. And if you find this interesting, you should think about taking more physical chemistry. There's a class I teach called Introduction to Physical Chemistry 266 that's taught block 2. So if you're interested in how physics helps us understand chemistry, that would be a good class to take. So we want to think about what processes are spontaneous. So does the reaction go forward? Does it go backwards? Or is it at equilibrium? So if it's spontaneous, we say it reacts in the forward direction without any input. So a process that once started proceeds on its own without a continuous external influence. So you don't have to put work in. So when you look at this process of having two flasks, one empty, one full on the left-hand side, the spontaneous direction of change, if you open the stopcock, would be for the gases to disperse evenly over both flasks. That's spontaneous. It would be non-spontaneous if you had those two flasks with the gas equally distributed on the right and you opened the stopcock and it went back to the left. So we know a lot from our experience in life what processes are spontaneous. Now let's think about why they're spontaneous. So this just shows you that one process that's spontaneous is rust. So we see a lot of rusting of metal, so of iron. It's a slow process, and so we don't want to confuse a process that's spontaneous with a process that's fast. So we talked about kinetics and how some reactions are slow and fast, and that has to do with the transition state energy or the activation energy in between reactants and products. What determines whether or not the reaction takes place is we're going to see a difference in Gibbs free energy in reactants and products. So it won't necessarily happen fast, but we'll understand the direction of change if we waited. Oops. So need to be reminded of some things you learned in Gen Chem 1. And the first is the idea of a state function. So a state function is just a function whose value depends only on where you are, the present state or condition of the system, not on how you got there. So that tells you that if you can find any path from reactants to products, you can determine the change in that state function. So enthalpy is a state function and entropy are a state function. So we're going to learn a lot about both of those in this chapter. So the enthalpy is the heat change in a reaction or process at constant pressure. So that's delta H. Entropy, I'm going to show you there's going to be two really important concepts from physics in this chapter. And one of them is that entropy really shouldn't be discussed as randomness. It should be discussed as probability. So we'll put more definition into entropy as we go along. Right now, what you've learned from Gen Chem 1 is that it's the randomness, that a gas system has more randomness, more disorder than a liquid, for example. And we're going to understand that a little bit better in terms of probability. So this is just showing you a process that is spontaneous. We use natural gas, which is at the bottom of the slide, CH4, methane. It's a primary component of natural gas. The reaction of oxygen, and in that process, a lot of heat's given off. The process takes place spontaneously, and you get water and carbon dioxide. You always have to spark that, so you have to have an electronic igniter on your gas stove or use a match on an old one, because there's a high activation barrier and you have to get it started. But once you start it, that reaction goes on its own. So the process of changing methane plus oxygen into CO2 plus water is a spontaneous process. So is it true that all processes that are exothermic are spontaneous? That reaction from this slide is at the top of this slide, and it is an exothermic reaction, so heat is given off. But do all exothermic processes occur spontaneous? So let's look at, for example, the melting of ice. That's called fusion. It's an endothermic process. Does ice melt? Yeah, ice melts if you're above a certain temperature, and we'll see how temperature impacts spontaneity. If you're below a certain temperature, the freezing point of ice, it wouldn't melt. So even though melting is an endothermic process, it can still happen spontaneously. Water can still vaporize spontaneously. That's also an endothermic process. N2O4 can form 2NO2, and that can happen at a certain temperature. So lots and lots of processes that are endothermic can be spontaneous. And so we need to think about what is the physics that determines if a process is spontaneous. And so we have to really understand the concept of entropy. So the concept of entropy, a change in entropy is the entropy of the final state minus the initial. That's always true for a state function, whether it's enthalpy, entropy, energy. And so when we look at how entropy depends on the phase, a solid has less entropy than a liquid. The solid, everything is held in its place. There isn't much disorder. When it goes to the liquid, the bonds are continually breaking and reforming, and so there's much more chaos. When you get to the gas, the particles can flow anywhere, and there's a lot of disorder. So going from left to right in this slide, there's an increase in entropy. For some reactions, there's an increase in entropy based on the number of particles. So the N2O4 reaction going to NO2, if you have more molecules on the product side in the gas phase, there's going to be more disorder, more locations, more ways for them to be distributed, versus on the left-hand side, N2O4, fewer particles, fewer places things can go. So if you change the number of gas molecules, an increase in number of gas molecules in a reaction will mean that the entropy of the system is increasing. This is a discussion about, it's not always quite that easy. When it's a reaction, that's pretty easy. When it's simply a phase transition, that's pretty easy. But when you have this situation where you have on the left-hand side a solid and a liquid, and then you make a solution out of the two, there's some increase in entropy, but then there's some decrease in entropy as well. So as the water molecules are pulled apart from each other, the ionic bonds are broken, that increases entropy. But it turns out this process of solvation, where the polar water molecules surround the cations and anions, that actually decreases the entropy a bit. So in general, the entropy goes up when a solution is formed, but sometimes it can actually go down depending on how much order is added in that solvation process. So entropy and probability. This is something I really want to make sure you understand. So Boltzmann's equation is this equation, S equals K ln of W. And W is defined as the weight. So I am going to move to the document camera for just a minute, because I really want to make sure that you understand this idea. Very slow. Okay, so what is weight? What is W? So entropy from physics is, if you look at a molecule, a molecular system, and you actually look at the particles, what is entropy? So entropy equals, this is Boltzmann's constant. He came up with this equation. And this thing is called the weight. And so what's really true is entropy is a measure of the probability of something happening. So let's look at having 4 pennies. So how many different ways with those 4 pennies could you flip them and end up with all heads? Well, this would have to be heads, no choice, no choice, no choice. So the weight of all heads is 1. Therefore, what's the entropy? Ln of 1 is 0. So that entropy of that is 1, which really is saying that however the system is organized, there's only one way to do that. Now let's just think about a more probable distribution. So let's think about having 4 pennies. And what's the probability of 1 head and 3 tails? So how many different ways could you flip the pennies and end up with 1 head and 3 tails? Well, given the pennies can be distinguished from each other, we have 1, 2, 3, 4. Maybe one student's flipping 1 penny. So you can tell the pennies apart. So when you flip the pennies, these are just the numbers of the pennies. So first case could be the head ends up with penny number 1. That's one possibility. But the head could end up with penny number 2, or penny number 3, or penny number 4. And so there are 4 different ways for you to end up with 1 head and 3 tails, because those individual pennies have that many options. Each could be one or the other, and one of them needs to be a head. So if you flip pennies over and over again, 4% of, well, 4 to 1. So every, well, you should get this distribution 4 times as much as you get all heads, because it's just more probable. It's not really necessarily more random, it's just more probable. So the weight for this is 4. Entropy is, K ln of W. You can look up Planck or Boltzmann's constant. It's in units of joules per K. It's in the back of your textbook. So the important thing is, when you think about entropy, it's really a probability thing. And so this is showing you the same thing, that the weight is the number of ways a state can be achieved. So if you think about it with pennies, I think it helps you understand molecules. So in a molecule, when you think about heads or tails, you're thinking about its location, its energy, its vibrational energy, all of those things that molecules can differ on. So the weight is the probability. The higher probability of a state, the greater entropy. Okay, so the third law of thermodynamics says that the entropy of a perfectly ordered crystal substance at 0 Kelvin is 0. So it's kind of like the all heads. If you take a sample, you slow down the gas molecules till they become a liquid, you slow those down till they become a solid, and then you slow those down so there's really no movement, except movement that has to be there, which you learn more about that in physical chemistry. then you would get this perfect order, and there'd only be one way to do that, and so the entropy would be 0. So what changes entropy? So if you start out at the left-hand side, temperature of 0 and entropy 0, you'll have a solid as you increase the temperature. As you increase the temperature, the atoms start to vibrate relative to each other. There's different ways for that to happen. So there's more ways to have those distributions. And so the entropy increases as you increase the temperature. Then when you get to the phase transition from solid to liquid, you have a big entropy change, go up on the y-axis, because you're going from particles that are held in their spots in a solid to their free movement. In a liquid, they're moving past each other and the bonds are continually breaking and forming. But then with a liquid, as you increase the temperature, it's going to be more kinetic energy, more randomness, more ways to do it. And so the entropy will continue to increase. So notice, it doesn't matter what the phase is, the entropy is always increasing with temperature. When you get to the phase transition from liquid to gas, notice there's a huge difference. So solid to liquid changed a lot, but liquid to gas changes a lot. There's a huge vertical change in entropy. And then when you get up to the gas, just like the solid and liquid, there's a continuous increase in entropy. So you add more temperature, more heat, the particles move with more kinetic energy. There's more ways for that to happen. So it continues to increase. This is just a table giving you some entropy, and your book has huge tables in the back where you always found delta H's of formation. But in general, the bigger the molecule, the more entropy it will have, and we'll look at some specific calculations. So what you'll get out of these tables is the actual entropy. So you won't get changes in entropy like you get changes in enthalpy out of that table. And that's because if we say entropy is 0 at 0, we can actually measure all of these additions of entropy as you increase the temperature. When you get to 25 degrees, you can actually have an absolute entropy value. So the values in the table for the standard state be the entropy of a mole of a pure substance. Our tables are for 1 atmosphere pressure and at a specific temperature, and our tables are for 25 degrees. So if you want to use those tables, you'll take the entropy of the products minus the reactants and end up with a delta S standard state for a process. So if you have a reaction, the products minus reactants, don't forget that each of these is entropy in joules per K per mole. So you have to multiply by the stoichiometric coefficients, which tells you the number of moles in your reaction. So we will use this equation when I do a couple problems after this lecture. So this is just doing one of those problems, so using this equation. So for the N2O4 going to 2NO2, we'd have to multiply 2 times the standard entropy of NO2 gas, subtract from that the standard entropy of N2O4. So you just go to the table, get those values, and end up with 175.7 joules per K, which we could have predicted it was positive because we're going from 1 mole of gas to 2. And don't forget the units. The units on entropy will always be energy per temperature, and temperature has to be in Kelvin, so our book will use units of joules per K. If you have a quantity, it will be joules per K, gram, mole, something. But here, this is just joules per K per the reaction. So the laws of thermodynamics will help us determine when something's spontaneous. The first law that we saw back in Gen Chem 1 when you did thermochemistry says that in any process, spontaneous or non-spontaneous, the total energy of a system and its surroundings is constant. So we use that to determine how much heat and work flowed in and out of a system as a change took place. The first law doesn't tell you anything about which way the energy will move. It's the second law of thermodynamics that says in any process, in any spontaneous process, the total entropy of a system and its surroundings always it increases. So that means the entropy of the universe always is increasing. So that's the same as saying we're going to a more probable distribution of things as time goes on. So this will be the second super important concept from physics. So the first one was that entropy is related to probability. This one is how it relates the second law of thermodynamics to our understanding of spontaneity. So if we have the delta S of the system plus the delta S of the everything else, so that might be a reaction flask you're carrying out your reaction in, and then everything else is the surroundings. So if we add the two together, in the second line they're just showing you it's easier to abbreviate, makes it shorter. The reaction will be spontaneous if the universe's entropy goes up. So if that sum is positive. If it goes down, it's non-spontaneous. The process won't happen on its own. You'd have to force it with some work, or the backwards reaction is spontaneous. If in the process of your system changing, delta S total is 0, then the reaction's at equilibrium, and it will be reacting forward and backwards in equal amounts. So when we think about how we can understand the delta S of the surroundings, so we've already thought about the system. When you form more gas molecules, you get more entropy. If you increase the temperature, you get more entropy. If you go from solid to liquid, liquid to gas, you get more entropy. But what about the surroundings? So the system or the surroundings entropy will increase just based on heat coming in or out. So if you have this little Erlenmeyer flask here and you carry out a reaction, if any heat leaks out, it's gonna excite the gas molecules that surround that in the air, and their entropy is gonna go up. If you have the opposite situation where your system needs to pull energy in from the surroundings, then you're gonna be cooling off the air, and the entropy of the air around the flask will go down. So from those experiments, you can determine that the delta S of the surroundings is proportional to the negative delta H. So it goes up if the system has a negative delta H. It goes down if the system has a positive delta H. So essentially what you're saying is if the system is losing heat, the surroundings is gaining heat. So it's going to be proportional to the negative sign of what happened to the system. It's proportional to 1/T, which you'll learn more about if you take physics. So at a higher temperature, the entropy will change less if you add the same amount of heat. You put those two together, you can find out with experiments that the surroundings entropy change is equal to negative delta H for the system divided by T in Kelvin. And so you learned in Gen Chem 1 that we chemists use a Gibbs free energy change to decide if a process is spontaneous. So this slide is super, super important because we want to confirm that chemists just use the laws of physics. They don't make up their own laws. They may act like they do, but they don't. So the delta G, if the process is carried out at constant temperature and pressure, your book doesn't focus on that, but it is an important concept. So this is only true if it's a process at constant pressure and temperature. So delta G equals delta H minus T delta S. So you use that equation a little bit back in your thermochemistry. And now if we think about from physics we know that the total entropy changes if the system's entropy changes and the surroundings. And we just went through a process of showing that the surroundings entropy change can be related to the system's enthalpy change. So delta S for the surroundings is equal to negative of delta H of the system divided by T. And then the second from last line is showing you that when there is no subscript, we're referring to the system. So delta S system can be replaced with just delta S. So when we go to this. Do they show you that? So that's not a hard, let me just put the document camera in just so you know exactly how they went from the last line to the last, or the second to last line to the last line. So I'm going to unshare this. And for some reason, it's taking a while. Okay, so they had given you our definition of a Gibbs free energy change. This is for constant pressure and temperature. So if we know that delta S total is equal to the system plus the surroundings entropy changes, and if we know that the surroundings can be defined in terms of the system, then we can say we drop the subscript on delta S system, we're referring to the system, and if we replace the surroundings with what the entropy change of the surrounding is in reference to the system's enthalpy change, we end up with this. So then if we multiply through by T and then multiply through by -1, we end up with negative T delta S total. And I'm going to change the order. So if I multiply this by -1, I get delta H, and I'll get a negative up front, the T delta S. And how does that relate to how we define delta G? That is our delta G. And so if the delta S total so the total entropy change of the universe is positive, because this is T in Kelvin, it will always be positive, then it will always be true that if the universe's entropy increases, delta G will be negative. And if you remember, I'm going to go back to the slides. Oops. Did I ever share this? Let me go back to the document camera, sorry. I don't think I actually ever shared the document camera. We'll go back to share. Okay, so this is, I don't think I was sharing this. So delta S total is system plus surroundings. Delta S is the surroundings we just said is equal to negative delta H over T. We're gonna now use a Gibbs free energy change, so let's see how it changes to or relates to a delta S total. So at constant T and P, all of this is true. So delta S total is gonna be delta S of the system. We drop the subscript, it's delta S of the system, minus delta S of the surroundings can be related to delta H of the system. So if we multiply through by T, we get T delta S total equals T delta S minus delta H. And then if we multiply through by -1, -1 times this negative gives us positive delta H, get a negative here. And what you see is negative T delta S total is equal to delta G. So if T is in Kelvin, you will always have a negative delta G if you have a positive delta S total. So now let's go back to our slides. Okay, so now we're sharing again. So that's what this slide is trying to show you, and that's a super important concept, that when we talk about delta G and how it relates to spontaneity, we're really just talking about the second law of thermodynamics. So that means that if delta S total is positive, delta G will be negative. That's our criteria. We say if delta G is negative, the process is spontaneous. If delta G is positive, the reaction is non-spontaneous. And if delta G equals 0, we're at equilibrium. So that's exactly the same criteria as if you were saying delta S total is positive, spontaneous, delta S total is negative, non-spontaneous, delta S total is 0 is equilibrium. So when we use a Gibbs free energy, we're really just using the second law of thermodynamics. This is now just showing you why it is like at the beginning when we said, when water melts, it's spontaneous if you're above a certain temperature. So when water melts, so if you melt ice, it has a positive delta H. So I think it's the second line. Oops, no, it's the third line because it also has a positive entropy going from solid to liquid. So if you have that process where you both have positive delta H and delta S, it's going to be spontaneous at a high temperature. And that's what we see with water going from solid to liquid. It's spontaneous if you're above the temperature of freezing. So we're going to use Gibbs free energy changes to decide if something's spontaneous. Just more easy, simpler than trying to think about the second law directly and getting delta S of the surroundings and making sure we understand what we're talking about. So when we get these out of a table, the standard state, remember when it has that little circle or not sign, that means we're talking about the most stable form of a substance. Our tables are at 1 atmosphere and our temperature is 25 degrees. And if we have a solution, everything's in 1 molar concentration when you take it from the table. So this is just calculating a delta G naught from a delta H and a delta S. And probably one thing you should note is that when you get the delta S's, so the negative 198.7, those are usually in units of joules per K because they're smaller numbers. Whereas notice the delta H is in kilojoules. So just make sure that you have consistent units before you add them together, like this slide is showing. So if we want to get the delta G, not for a reaction, the other way to do it is to go directly to the delta G's of formation in your table. And just like delta H's of formation, you can use those to get the delta H of a reaction. A delta G for a reaction is add up all the delta G, so formations of the products, and subtract the reactants, remembering to multiply by their stoichiometric coefficients because each of these guys is in per mole. This is just a little table. Your book has a huge table at the back. It's the same table that you got heats of formation out of in Gen Chem 1. So this is just calculating a delta G. So they went to the table, got the value for iron solid, which is 0, carbon dioxide gas, which is negative 394.4, iron 3 oxide, negative 742.2, and carbon monoxide, negative 137.2. Multiply them by the stoichiometric coefficients, which are the number of moles, and so you end up with units of just kilojoules. And this particular reaction has a negative delta G 29.4. So because it's negative, that would mean if you put everything in here, in this case, all the gases in one atmosphere, the reaction would go forward. So when it has the little not sign, it tells you whether or not the process is spontaneous under standard conditions. We don't usually put things in our reaction under standard conditions, so everything at 1 atm. So we need an equation that will allow us to determine a delta G at any pressure or concentration. And so this is the equation you'll use. It says delta G for any conditions is equal to the standard state delta G change plus RT, R is the gas constant, T is the temperature in Kelvin, and then natural log of Q. So Q is just the reaction quotient from our chapter 13. And so for this particular reaction, it's the pressure of ammonia squared divided by the pressure of nitrogen and the pressure of hydrogen cubed. And each of those has to be in units of atmospheres to go with the numbers that come out of our book. So calculating this for a reaction, we want to know, we are forming ethylene in this reaction, we're at 25 degrees, but we want to know what's the delta G going to be if we change the pressure. So increase the pressure of the reactant, decrease the pressure of the product. We know that's probably going to, from Le Chatelet's principle, make the delta G more negative than if they were each at 1 atmosphere. Let's see if that's true. So the delta G standard state they got from doing delta G's of formation from the back of the book. So this reaction is not spontaneous at conditions of 1 atmosphere for each of the gases. So it's delta G is 68.1 kilojoules and it's positive. So when we put the pressures in, they do that part. Squared the hydrogen, yeah. Oops, I think, yeah, that shouldn't be a 2 there. Should be 0.1. So the pressure of the acetylene of 0.1, and then the pressure of hydrogen is 100 atmospheres. So the denominator here should be 100 squared. It shouldn't be 1,002. And hopefully, let me just check and see if they did the math right. They did the math right, they just wrote it wrong. So you get the natural log of 0.1 divided by 100 squared, put it into the equation. They're using the gas constant in joules per K mole and converting over here on the far right-hand side, converting the joules and the gas constant into kilojoules, adding them together and getting 39.6. So it's become less positive, like we knew it would from Le Chatelet's principle. So we've increased the pressure of the reactants, decreased the pressure of the products from the standard states of 1 atmosphere. And so it makes sense that it becomes more positive. It's going in the direction of becoming spontaneous forward. So free energy and equilibrium. So when the reaction quotient is mostly reactants, Q is much less than 1. Yeah, so this is just showing you, and you would already know these things from chapter 13, just by looking at the Q in Le Chatelet's principle. So this is telling you which way the reaction goes based on the delta G. So if the delta G ends up negative, the reaction will go forward. If the delta G ends up positive, it will go backwards. And this is just showing you in a visual way. You're going to the lowest value of Gibbs free energy, which is the same thing, if you think about it from physics, as saying I'm going to the maximum value of entropy. So at that minimum place, that's where the reaction's at equilibrium. So it's going to go spontaneous forward or spontaneous backwards until it reaches that minimum value. So at equilibrium, delta G equals 0. So we can actually measure delta G's and determine equilibrium constants, which is often an easier way to do it than measuring all the concentrations at equilibrium. So if we take our equation that we've been using, if we set delta G equals to 0, because that's what equilibrium would be, and then that would mean Q equals K, and rearrange that equation, that says if you can get the delta G for the standard state, it's equal to negative RT ln of K, and you can get the equilibrium constant for a reaction. So this is asking us to get the Kp. So in this reaction, Kp would simply be the pressure of CO2. So if we add up delta G's of formation of products, subtract reactants, we end up with a delta G naught of plus 131.4 kilojoules per mole. If we plug that into this equation and solve for K, we get a very, very, very small K value, 9.2 times 10 to the minus 24. And that is the last slide. So the two important concepts from physics were entropy is really a measure of probability. And the second one is that the chemist's criteria, when delta G is negative, a process is spontaneous, is really just using the second law of thermodynamics, which states that when the entropy of the universe increases, a process is spontaneous. So those are the two super important physics concepts that I hope you got out of this lecture.